Hi everyone, welcome back. In this video, we are going to understand one of the most important concepts inside SQL Server performance engineering, pages. Now, when developers think about tables, they usually imagine rows stored directly inside a database table. But internally, SQL Server does not store data directly as tables. It stores data inside structures called pages. And understanding pages is extremely important because almost every database performance problem eventually becomes a page access problem. Indexes reduce page reads. Table scans increase page reads. Large rows consume more pages. And page splits can severely impact performance. So in this video, we'll understand what pages are, how SQL stores rows, how indexes reduce page access, and why page reads directly affect performance in D365 FO systems. What is a page? Let's begin with the most fundamental concept. A page is the smallest physical unit of data storage in SQL Server. Every piece of table data is ultimately stored inside pages. One page is exactly 8 kilobytes in size. That means 8 kilobytes, or 8,192 bytes. Now, this is extremely important to remember because SQL Server reads and writes data page by page, not row by row, not table by table, page by page. So whenever SQL Server executes a query, the actual cost largely depends on how many pages need to be read from memory or disk. Tables and records. Now, logically, we say that data is stored inside tables. For example, cust table, sales table, sales line, perch table, and so on. But internally, SQL Server spreads those rows across multiple pages. As the number of rows increases, page 1 becomes full, then page 2, then page 3, and so on. So a large table may actually consist of thousands or even millions of pages underneath. And importantly, one page can store multiple rows depending on row size. Page layout. Now let's look at how a page is internally organized. A SQL Server page is not entirely available for row data. Some space is reserved for SQL Server's internal management. At the top, we have the page header. This is approximately 96 bytes. The page header stores metadata such as page identifiers, previous and next page references, allocation information, and internal SQL metadata. Then comes the actual row data section. This is where SQL stores the table records. And finally, at the bottom, we have something called the row offset array. This stores the positions of rows inside the page. Together, the page header and row offset array consume around 132 bytes of overhead, which leaves approximately 8,060 bytes available for actual row storage. Row size calculation. Now let's understand how row size affects storage. Suppose we have a sales line table with fields like sales ID, item ID, line number, inventory transaction ID, and sales quantity. Each data type consumes storage bytes. For example, nVary fields consume around 40 bytes, integers consume 4 bytes, decimals consume additional bytes, and SQL Server also adds internal row overhead. So in this simplified example, one sales line row is approximately 140 bytes. Now remember, the number of rows per page depends entirely on row size. Rows per page. Now let's calculate how many rows fit into one page. We already know one page has around 8,060 usable bytes, and one row is approximately 140 bytes. So, 8,060 divided by 140 gives us around 57 rows per page, which means one page can store roughly 57 sales line records. Now this becomes extremely important in large systems because SQL Server performance is heavily influenced by how many pages are required to store and retrieve data. 100,000 rows example. Now let's scale this up. Suppose our sales line table contains 100,000 rows. If one page stores around 57 rows, then SQL Server requires approximately 1,754 pages to store the table data. And since every page is 8 kilobytes, the total storage becomes roughly 13.7 megabytes. Now this may not sound huge, but remember, SQL Server works by reading pages during query execution, so query cost depends heavily on how many pages must be accessed. Query without index. Now let's look at a query without an index. Suppose we execute this X++ query. Select sales line where sales quantity is greater than 50. Now imagine there is no index supporting this filter. What does SQL Server do? It has no shortcut, so SQL Server must scan every page in the table. That means all 1,754 pages must be read, around 13.7 megabytes of data must be processed, and every row must be checked individually. This is called a full table scan. And as table size grows, this becomes increasingly expensive. Now let's compare this with an indexed query. Suppose we search using sales ID, and sales ID has a proper index. Now, SQL Server does not need to scan every page. Instead, it uses index pages to navigate directly to the required data. This works very similarly to a phone book. At the top, we have a root page. The root page contains ranges that point to intermediate pages. Intermediate pages narrow the search further. And finally, leaf pages point directly to the exact data rows. So instead of scanning all rows, SQL Server performs a tree traversal. This is why index lookups are extremely fast. For 100,000 rows, a full scan may check all rows, but an index lookup may require only around 17 navigation steps. That is the power of indexes. Analogy. A simple way to understand this is with a real-world analogy. Without an index, finding a row is like checking every single house on a street to find one person. But with an index, it becomes like checking a society register. First the block, then the floor, then the apartment number, and going directly to the correct location. That is exactly how SQL indexes reduce page reads. Performance comparison. Now let's compare the actual impact. Without an index, SQL may read around 1,754 pages and process around 13.7 megabytes of data. With a proper point lookup index, SQL may read only 2 or 3 pages, which may be only around 16 to 24 kilobytes of data. That is an enormous reduction in physical I/O. Range queries may still read more pages, but usually far fewer than a full table scan. And this is why indexes are one of the most important concepts in database performance engineering. Page splits. One more important concept is page splits. Suppose a page becomes completely full. Now, if SQL Server needs to insert another row into the middle of that page, it may split the page into 2 pages. This operation requires moving rows, updating pointers, and additional I/O operations. Page splits are expensive, and excessive page splits can lead to fragmentation and performance degradation. Later in this course, we'll study fragmentation and fill factor in much more detail. Closing. So the key takeaway from this video is, pages are the real physical unit of storage and I/O inside SQL Server. Performance is heavily affected by how many pages exist, how many pages are read, and how efficiently indexes reduce page access. For large D365FO systems, performance engineering is largely about minimizing unnecessary page reads. Because fewer page reads means less I/O, faster execution, lower resource consumption, and more scalable applications. In the next video, we'll go deeper into indexes and understand exactly how SQL Server uses B trees internally for data retrieval. So, I'll see you in the next video.